So states and 67, it's the same age. My level is special. And then by the go in quiz, and I wonder what is stuff 9 south. I said, like, it's gonna be like, I will say, because if I say. What if we go and we go?
I went down here like.
This isn't even going over my head, this is like going under my car, like, it's like nothing. It's like nothing. It's more like.
Walked to LA to bed.
Like titration or something like.
Like.
I'm not. Some people find it just like.
Smoke check.
Something like. I went on these.
Ate Subway.
Oh,
it's not.
Yeah.
COVID is COVID. Like the best little small favorite. Yeah, you seem like making the reality.
Yeah. What's your make? That's a lifestyle. I did nothing at all because we were introduced to project. That's so nice. Like we have to write our. Like.
Sponsored by Calc.
Yesterday we had like.
All right, guys,
That's what I do.
let's go to page 19. Okay, guys, page 19. We have one more topic to go over, and that is volume by cross section. So far, all the volume problems that we've done have been rotating about an axis. You know, whether there's a gap, whether there's not a gap, whether it's this method or Washer method, there's always that rotation feature. So whenever there's rotation involved, we know there's always circles involved, and that's why our formulas so far have that pi r squared built into the volume formula, right? Because these are all the everything from this method and Washer method have all had circular cross sections. So what that just means is if you were to slice the object at any point and you open it up, it's always going to have a circular ring, whether it's a circle within the circle, like a ring-shaped object, or a cylindrical circle. But everything is circular based, right? So that's why that pi r squared is coming into play. So again, cross section is shape that results if we cut the object in half and look at the resulting shape sideways. Okay, so circular area, either pi r squared or pi big R squared minus pi little r squared. But now, what if the object that we're building or the volume that we're trying to find is not for an object that has a circular cross section, but what if it had different shapes? What if you were to slice the object, you open it up, it ends up being a square or a triangle or a semicircle? So we're going to be building these cross section area on top of a base. So we're no longer going to be rotating around an axis. We're going to be building on top of a base. So these objects are really kind of hard to draw. And we don't have to worry about drawing it. We just have to be able to figure out the information that we need and then just plug in the formula, right? Before, we would always say, okay, connect the distance between your axis of revolution and your further curve or your outer curve, and that will be your radius, right? But now that distance is now going to be called the base length of some dimension that we're going to create. So
So in this case here, this is a shape where we have a shaded region, and then we're building differently sized squares on top of this base. Okay, so this is what the resulting object would look like. Okay, it's hard to describe what this object is. It's not really a true geometric shape like like a cone or a cylinder. It's just some object that has a square cross section over the interval of this from one bound to the other.
So R becomes.
Right, so the R that we're gonna gather will become the base of whatever formula we're building. So we're still gonna find the information very similar to how we did area and how we draw our radius. But then after we find that radius length, we're gonna put it into a different formula rather than the disk method or washer method formula. So it shouldn't feel all that different. It's just we have to adapt to the different formulas. But in terms of information gathering, we're going to be gathering the information very much the same way that we did with this method and area. So here are the different shapes that we can create after we find that one of the length of this object. We can build a square on top of a shader on top of a base. We can build differently defined right triangles. We can build a rectangle, we can build an equilateral triangle, we can build a semicircle, but they all involve just some formula, right? So once you find that one length that we're looking for, then it just goes into the formula and the rest gets plugged to the calculator. So what we're going to do is we're going to start off by finding the volume of this particular shape that we see here. Okay. So let's look at example 1. It says find the volume of the solid if the base is bounded by the curve y equals square root of 1 minus x squared. Now this is just going to be a semicircle, but a semicircle is going to be cut off by just in the first quadrant. So it's going to be a quarter circle actually. All right, so now the shape of your base of your shaded region has no bearing on what you're trying to build. Okay, it just so happens it just happens to be a quarter circle, but it's not had nothing to do with what we're building on top of this base. It's just okay. So here's square root of 1 minus x squared. Now the cross section are squares. So we know ultimately we're going to be relying on this square formula parallel to the y-axis. So this is telling us how to draw our base length. Okay, remember how when we did our radius, we would have a very specific way that we drew the radius. It's always perpendicular to our axis of revolution. So it could be a vertical radius, could be a horizontal radius, but here they're telling us how to draw that length parallel to the y-axis. So the y-axis is this way, right? Vertical. So parallel means I got to keep that same direction. So I'm going to extend from one boundary to the next vertically. And instead of calling this the height of a rectangle, instead of calling this the radius of a circle, we're going to call this the base length of one of whatever shape we're trying to build. So the base length is just top minus bottom. Okay, what's the top of my length?
1 minus square root of 1.
Okay, square root of 1 minus x squared. Minus what's the bottom touching the 0? There we go. There's my base length. We're going to find bounds the same way that we did area or disk method. What's the furthest left x value that we see? Oh, and by the way, if we're doing a vertical base, then we're going to be doing top minus bottom. So top minus bottom is the easier one where there's no need to rewrite your equation and your bounds are just from the furthest left to furthest right. Okay. What's the furthest left you see?
0.
0. What's the furthest right you see? Okay, it's going to be 1. The way that we know it's 1, if I set the root 1 minus x squared equal to 0, that intersection with the x-axis, if I solve for x, I get plus or minus 1. -1 is over here, +1 is over here, so +1. Okay, from here, let's build the area of a square. So we're kind of building our information, right? We start off with a one-dimensional unit, then we're moving on to a two-dimensional unit. Before we would do pi r squared, but now we're going to just do base squared, right? We're building a different shape here. We're not building a circle-based object. We're building a square-based object. So now, once we have our area, then we just put it with our integral notation. So the integral notation will just give it that third dimension that we're looking for. Okay, and here we don't do pi. We don't do pi because this is not circle-based. I know you're seeing a semicircle here, but that is not, and that's no bearing. It's just a coincidence that this is a semicircle. We're building squares on top of this base, right? Differently sized squares. Right, so the integral from 0 to 1, my area, which if I clean that up, it's just 1 minus x squared dx. And that's it. So whatever we get for volume, this is what we're finding. We're finding the volume of this object here. Okay, we can use our calculator. We're just going to enter this in into the calculator here. Two-thirds. So our units will just be 2/3. No pi. It's just 2/3 units cubed. Still volume.
Square, like.
It says
Oh.
cross sections are squares.
Oh.
So you're always going to be told which shape you're going to be targeting. And then you're also going to be told very explicitly how to draw your base length. It's either going to be horizontal or vertical, but there's multiple ways to say this. They can say parallel or perpendicular to the x or the y axis. So don't just assume that, oh, if I see parallel, that it's going to be vertical. It depends if it's to the x or to the y axis. So just make sure that you spend time to convince yourself that that you're staring at a vertical or a horizontal base, because that's going to determine how you want to build your equation. But once you find your base, then it's just formula, right? So we're not really it's not going to feel any different from this method in terms of gathering information, right? You're still gathering the same information, but instead of calling it radius, you're calling it base. And then you're just plugging the different formula. And we never have to worry about drawing the graph. We just have to worry about getting that base length, putting into the appropriate formula, make sure our bounds are in terms of the right variable, make sure our expressions in terms of the right variable, and the rest of the calculator work. All right, let's go to page 20. All right, find the volume of the solid if the base is bounded by y equals x squared and the line y equals 4. So let's sketch our graph and figure out that shaded region. Cross sections are isosceles right triangle. That just tells us what formula we're going to be targeting once we get to the base. Hypotenuse lie on the base. So here we have it. Isosceles right triangle with hypotenuse of the base. The formula is 1/4 base squared. Parallel to the x-axis. Let's pay attention to that. Parallel to the x-axis. Which direction is that? Horizontal or vertical? Yeah, x-axis is this way, is sideways. I want to be parallel to the x-axis, so it's going to remain sideways, which means I got to do right minus left. So if I do right minus left, I got to spend time rewriting my equation. My equation is not in the correct form. So here we have our horizontal rectangle, but this is not the height of a rectangle. This is not the radius of a circle. This is the base length of a triangle that we're building. So we're building a triangle on top of this base, right? And it's just going to be a strange looking object, but we just have to be able to get that information to put into the formula. Now, our equation is not in the correct form, right? I need to rewrite this so that I can solve for what? X. So if I solve for x, I get x equals what?
I mean, like you.
No.
Root y. Now, what happens with the equation here? If I take the square root of both sides, I get plus or minus root y. So that is going to tell us, that's actually telling us the two different equations here. You got the positive root y here. You got the negative root y here. And that allows you to have two equations to kind of work off each other.
Y is always going to be positive, right?
Y is always going to be positive. That's right. Yeah, it has to be because it's under the square root. Okay, let me just help us visualize this a little bit better here. So I'm going to highlight the square root of y in one color, and then the negative root y in a different color here. All right, so we'll do right minus left. And we'll call it the base length. Okay, what's the right endpoint of my base length touching? Root y. Minus, what's the left endpoint touching? Negative root y. It's not going to cancel out, right? It's actually going to end up adding to become 2 root y. We have one dimension. Let's get it up to a second dimension here. Isosceles right triangle with hypotenuse on the base. So that's 1/4 base squared. So my area is 1/4.
Wait, do we have to memorize all these? Or?
Yes, we do. But here, let me just kind of talk a little bit about that. All your formulas will be base squared. Your area is base squared. Right triangle is base squared. Isosceles right triangle is base squared. Semicircle is base squared. Equilateral triangle is base squared. The only thing that we have to adjust for is what? The coefficient, right? So if its leg on the base is 1/2, isosceles is 1/4, equilateral triangle is √3/4, semicircle is pi/8. So you just know that, okay, it's going to be base squared. I just have to figure out what the appropriate coefficient is for my formula. Okay, volume. We can clean this up, or we can put it into the calculator. If I clean it up, it's less things to plug in. I can do 1/4 times 4y. Which just ends up being what?
Y.
Just y, right? So I'm just doing the integral from, okay, remember, we're dealing in terms of y here. So what's the lowest and highest y value? 0 to 4. No pi in front. We're not rotating around anything. Any questions here?
Perpendicular to y-axis means parallel to x-axis, right?
So perpendicular y-axis is vertical. So perpendicular must be in what? Horizontal. Yeah, so yeah, these mean the same thing. All right, I'll try example 3. It should feel very similar. You're actually going to get the same base. It's just a different shape that you're building on top of that shaded region. So we talked about how we never, because there's no rotation involved, most of the time you're not going to have any pi in your answer, except this one case. Here we're building semicircles on top of a base, and so because of the fact that it's a semicircle, there's going to be a pi that's going to be involved, even though there's no rotation going on, because the shape is circle related. That's why there's a pi involved in the answer, not because there's a rotation. Okay, any questions here? All right, let's look at example 4. We're going to need some help from our calculator here. Let region R be the area enclosed by the function natural log of x and 1/2 x minus 1. So we have the natural log of x, that's the curve. You have the 1/2 x minus 1, that's the linear. If region R is the base of a solid such that each cross section perpendicular to the x-axis, so that tells us what direction to move in. Isosceles right triangle with leg on the base. So we know that's going to be 1/2 base squared. Find the volume of the solid. Okay, so first things first, let's figure out which direction that we want to draw the base. Is it going to be a horizontal or a vertical? Yeah, so we have x-axis being horizontal. So vertical is up and down. Okay, but we do need our calculator so we can actually figure out where those intersections are. So let's practice doing that. I'll just do zoom 6 here just to see what my graph looks like. Okay, so that little small area there, I'm going to draw a box around it so I can kind of zoom in. So if I do zoom 1, I'm going to just try to imagine where the upper corner of my box will be. Hit enter once, and then don't hit enter until you see the box formed. Okay, I'm going to do intersection twice here. Second trace 5. I'm going to go after this point first. So just pick a point that is on the curve, close to the intersection, hit enter. Pick a point on the line that is also close to the intersection, hit enter. So then the calculator will just look for the closest intersection. It's going to look for this one, not this one, because we're closer to this one here. So we only care about the x value, so 5.356 or 5.357. The other one, second trace, you got to repeat the process again. And so I'm pretty close to the intersection now, hit enter. On the line, I'm pretty close to the intersection, hit enter again. I should find that left intersection for me here. 0.464. Our base length is top minus bottom. Top is sitting on the natural log. Bottom is sitting on the 1/2 x minus 1 here. Make sure you protect the bottom from the negative there. So as a reminder, you got to distribute that negative through. Okay, so our area is 1/2 base squared. Now the volume, we just insert that into the integral with the bounds. And the rest is calculator. Okay, any questions here? Okay, so what I have in the remaining pages are just a mixture of, these are just FRQ problems from past AP exams. That's a mixture of disk and washer and cross section. So let's do it page 21. Start there. Keys are attached for all these problems here. Let's read. Okay, so it says let R be the region bounded by the graph y is equal to 2x minus x squared. That's the curve that we see here. Looks like a bell-shaped curve there. And the horizontal line y equals 2. Let S be the region bounded by the two horizontal lines and the curve. Find the area of R. So area is just top minus bottom. All we need is to find the bounds. And then we just do vertical rectangle, right? All right, so try that. You're going to have to put the e to 2x minus x squared in the calculator, as well as the y equals 2. Find those intersections, and those intersections will be the bounds that you need for your area formula. Again, the area formula is just the integral, top minus the bottom, dx, right? There's no squared, there's no pi r squared, it's just height. We're accumulating the height, infinitely thin heights from one end all the way to the other end. Okay, 0.446 is my first intersection.
To graph like an x equals hypothetically, like how would I do that? Because y would be on different.
You can't graph x equals.
Okay.
If you want to find where the curve is at that x value, just plug the x value into the function, and you can find that y value.
Okay.
Yeah, but you can't. Yeah, this calculator won't allow you to graph a vertical line. My second intersection is at 1.554. My top graph is the e to 2x minus x squared. My bottom graph is the y equals 2. Subtract that. That's my height component. I got my width component. Accumulate that area or that height and width component over the course of the entire interval. And my answer is the area of region R. Part B says find the area of region S. So one way I think a lot of students want to think about region S is, well, maybe I need to create 3 separate intervals, right? Maybe I need to find the area of this region, because there's a top minus bottom. The second region here is a rectangle, top minus bottom there, and then another area there, and add those 3 together. But maybe there is I mean, that's perfectly fine. But is there another way that we can find region S that could be more efficient? Yeah, so why don't we find the area of this entire region here? And then that will give us the region of R plus S. Right, we do top minus bottom for that region. And then we just subtract R, and if we subtract R, then we're left with S. So I think that would be more efficient. But it's not wrong if you want to split up into individual, 3 separate parts, but this will save a little bit of time. But we do need to find the intersection between the curve and y equals 1. That's at 0. So from 0 to whatever that value is, we'll find top minus bottom there. Once we find that region, subtract out R. For part C, it says, write but do not evaluate integral expression that gives the volume of the solid when R is rotated about the line y equals 1. So here I have region R. Rotate that about the line y equals 1. So is this method or Washer method? Watch it, right? There's an obvious gap there, so we know we have to create a big radius, a little radius, the big R squared and that little R squared between the 2 bounds to set up that interval if that's our volume. Okay, so your homework is in your calendar. This will be the homework from the textbook. Oh, I'll send out a reminder about this, but I made a mistake when I was writing out the assignment. Not number 1, but starting with number 3. So. So for your cross-section homework, it's going to be page 610 to 612, numbers 3, 5, 7 to 14, and then your AP practice 1 through 8. I made that adjustment on my key, and I'll send out a reminder this afternoon that you're not going to do number 1, you're going to do number 3. 3, 5, 7, 14 is also the AP practice. All right, so get your folks. The key right now, so I'm gonna upload that later today. I'll send out a reminder when I have that up for you. Yes, it is. It's everything. We're done after this.
Crazy. Oh, yeah, we're going. I could be us. For free.
The good part is that we don't get out at like 3:30 because
I know. This can actually be crowded soon. Like, you don't understand how much you're going to this. It's probably disgusting.
Can I recover